Hey, it's Mr. K doing a video for AP Physics 1 with elastic collisions. Now for Physics C mechanics, go ahead and look at this too. We've got two things here. They're going to hit each other. As long as they hit each other, then it's good, and they don't lose energy. We can work with what we're about to derive. In this case, it's going to be a shortcut, but make sure you know how to get there because you need to know what cases you can use and what cases you can't. So this case where you have an elastic collision, no energy lost. In class, we have any elastic collisions, we always lose energy. But if you look at air molecules colliding, those do not lose energy. Those would be elastic. It's the Coulomb's force trying to repel each other. So you don't lose energy to heat and sound because sound is just a wave that travels through the air. It's this longitudinal wave that compresses through the air, and then heat is actually the movement. If you add heat to something, it's going to raise the temperature. It's going to be the movement or the kinetic energy of those molecules themselves. So we really don't lose that. So let's get started. We have a collision, so we're going to work some momentum. That means that we're going to take the momentum of the first one and the momentum of the second one. And we're going to add those together. I don't care which way they're moving because if we apply negative velocities, it will make these terms negative. So don't worry about that too much. Just momentum, momentum. Make sure you do it in one dimension. We're going to do this one time each for multiple dimensions. But we're just going to worry about one right now. After the collision, they're going to go bouncing off M1, V1, M2, V2. But we're going to prime them because we're going to show, hey, something's different. And that is our base momentum formula. So looking at this, we have two objects moving afterwards, after they collide. And let's just make this a little bit nicer to work with our kinetic energy. I'm going to move these M1s to the same side. So M1, V1 minus, move that over, M1, V1 prime. And on the other side, we're going to take that M2, V2 that's still there. But we're going to move this one over and say minus M2, V2. The first one is prime, that's that guy. So one more step, we call this factoring. We should all be familiar with that. Makes our world a little bit easier. And you're wondering why the heck I'm doing this. Well, I'm going to show you in just a second. There you go, look at that. So we have this nice M1 equation on the left side. We have this nice M2 equation on the right side. They're equal to each other. And we're going to use that in terms of kinetic energy to give us a little bit of a shortcut. So if we talk about the kinetic energy before and after this collision, we have some 1/2 m1v1 squared. It's moving beforehand. It could be still, but we're still going to write it down. We're going to add that to the kinetic energy of m2. So 1/2 m2v2 squared. And after the collision occurs, we have some kind of 1/2 m1v1 prime squared, because remember it changed. And we've got some 1/2 m2v2 prime squared. Fantastic. Looking at everything here, you say, oh, well, Mr. K, you can cancel out all the 1/2s. And I say, yeah, you can. You can take the purple pen and you can create or cancel out all these 1/2s. Now, you also say, hey, we can cancel all the m's. And I'm going to say, no, you're wrong, because remember, these m's could be all different. Yeah, so you can't do that. But what you can do is you can move all those m1s to the same side, much like we did over here, and all the m2s to the other side, which is what we did over here, except that the v's would have a square on them. So if I wanted to skip my little algebra step, because I know it's going to end up the same way like that, I am just going to put down v1 minus v1 prime, and these are going to be squared on the left side, and I'm going to say m2 with the v2 prime squareds on this in this parentheses here. Cool stuff, right? So there's another step that we're going to do here, a little bit of algebra. Look, we have differences of squares. That's amazing. I wonder what technique we can use. So we're going to rip that apart, and we're going to say v1 plus v1 prime and v1 minus v1 prime. And we're going to double check to see if we can put that back to the original by foiling it out. So firsts, good. Outers, inners, those cancel out, and then lasts multiplied together would give us this. And my dog figured out how to throw her own ball with the ball thrower. That's fantastic. Do the same thing on the right side. We're going to have v2 prime plus v2, and then we're going to say v2 prime minus v2. So we have the differences of squares here. And let's double check if we can go back to the original firsts. Give this that. Outers, inners cancel out, and lasts, they'll give us this right here. So the last thing we're going to do is we're going to utilize something called division, and we're going to divide two equations, particularly this one divided by this one, because if you look, I've got m's, I've got v1 minus v1 prime, I've got v1 minus v1 prime, those are the same, and these are the same. And so just to do a little math thing, if you divide one side by a number, you must divide the other side by that same value. And so if we divide the left side by m1 v1 minus v1 prime, which is just this stuff, I need to divide the other side by the exact same thing, but good thing it's equal to all this stuff. Sweet. And so we say, all right, cancel, 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 and cancel, cancel. And we get this nice, pretty equation. It's a very elegant solution right here that says that if we sum up the velocities before and after of an object in a collision with another object, the sum of these two velocities for one object should equal the sum of the two velocities for the other object before and after the collision. And we can just do a simple test of that and say we have the say we got those two red and blue Pasco cars that we use, and if we have them unmasked and we roll one into the other, let's say this is the red one, this is the blue one, and they're the same mass since they're unmasked, and if that red one comes in with some incoming velocity v1 and this blue one has some velocity v2, but let's say that it's currently 0, we know that when the red car comes in and hits the blue car, the red car should stop and the blue car should go. And this is, all due to Newton's third law, the equal and opposite forces. So the force to stop the red car is the exact same force to start the blue car, so it's going to have the exact same acceleration for the exact same time. And so really we should just see these velocities switch if it's a perfectly elastic situation, which in class we lose a little bit, but for the most part we keep it. So just look. If we say, all right, the red car has incoming velocity v1, we can add that to its v1 prime, which we don't know. The blue car has velocity v2 plus v2 prime, the velocity afterwards. We know that the starting velocity is nothing for the blue car, which means that the red car, which has velocity in the beginning, should lose all of it in the end in order for the blue car to have the same velocity as the left side in the beginning. And so that works out. So anytime you have an elastic collision, no matter the masses, you can kind of shortcut it by using this equation. If and only if you know where this equation comes from. You cannot use a tool unless you know the origins of the tool. So be careful with that. Don't get mixed up. This is probably the only time that I'm going to have you memorize something besides vocabulary terms. But yeah, this equation, really good for elastic collisions of any mass. Make sure you set this up first, and then you can utilize this guy because it uses kinetic energy, the conservation of kinetic energy, to get to it. All right, that's it.